Good morning, everybody. My name is Andrew Worth. I'm an artist working out of central New Jersey. For the last 6 or 7 years or so, I've been using Turing Patterns as a framework for many of my paintings. And this morning, I will be talking about what Turing Patterns are, how you can create them in Photoshop, a little bit about why that happens or why that works mathematically, and then how I've used Turing Patterns in my artwork. So first, let's talk about Turing Patterns. You're probably all familiar with Alan Turing. That's known for his work with theory of computation, artificial intelligence, and code breaking. But late in his life, he wrote a very influential paper called The Chemical Basis of Morphogenesis, which posited that certain kinds of reactions could occur when you have two or more morphogens, or substances, that diffuse in space, and they interact with each other in just the right way, called a reaction diffusion process. And if you have certain conditions of activation and inhibition, then you could form patterns like these, which are called Turing patterns. It has been theorized by Turing and many others that this type of process could be responsible for a lot of the shape generation in nature, especially pattern formation, like the stripes on the zebra, or these great patterns on the giant pufferfish, even possibly limb formation in embryo. It turns out that creating these patterns is very easy in Photoshop. If you start with a grayscale image, for instance, and you do the following over and over again, you blur and sharpen, then I have a few parameters, sample parameters listed here, but you can play around with it and try other parameters. You will get Turing patterns. The parameters you choose will affect whether or not you get a pattern, so you might end up with just a gray scale, a solid gray image. The parameters will also determine the scale of the pattern and the speed with which it might reach equilibrium. Because blurring and sharpening hundreds of times is a real drag, in Photoshop, an easy way to do that, make it easy, is with macros. Oops. So here's an example. Let's see if it's going to start. Okay, so what you do, I started with a solid image, or a noise, a random noise, and then I apply the Gaussian blur filter with a radius of 5. And then I go back and apply another filter in Photoshop, or really any image editing tool, and do unsharp mask. Amount of 100, radius of 10, threshold of 0. That's one step. Then I have a macro, which I can run over and over and over again. Blur and sharpen, blur and sharpen, blur and sharpen. Do it a bunch of times. And then I have another macro, blur and sharpen times 10, which runs that process through 10 times. And what will happen is, if you have your parameters set right, you'll end up with something looking like this. Here's it running 10 times. And eventually it'll stabilize and you'll have a Turing pattern. Now, why does that work? That was what I was interested in trying to figure out for my paper, is why is this process, which has been known for a long time, result in what are Turing patterns? Now, typically, there are many authors who've written models of reaction diffusion. This is sort of the generic model, where what you'll have is a series of one or more partial differential equations which describe how the concentration of a substance, here U, changes over time proportional to the gradient of the concentration of that substance. Plus, that's the diffusion component, plus, plus a reaction component. And the reaction component has to be a nonlinear function that accounts for interactions between the morphogens. So it accounts for things like one morphogen interacting with another and causing some kind of chemical change, or it deals with the inhibition of the growth. The spread of one morphogen might inhibit the growth of the other morphogen. And if that function is just right, you'll have the right kind of nonlinear reaction function to get a Turing pattern. So for Turing patterns to form, you need to have short-range activation or a positive feedback and long-range inhibition. And note that this left-hand side here, the diffusion component, if you were to write that as a discrete time step function, the solution to that can be expressed as convolution of an image function with a Gaussian. And speaking of convolution of image functions with the Gaussian, let's take a look at the mathematics briefly of blurring and sharpening. In my paper, I have this written out with equations, but for the presentation, I wanted to work with images to make it a little easier to follow. Let I be the image function, basically a function of x and y that says the color of a pixel at position x and y. To blur the image, what you do is you convolve that image with a Gaussian kernel. Here it's shown as a one-dimensional Gaussian, but in Photoshop it would be a two-dimensional Gaussian. That's the first step, Gaussian blur. The next thing you do is to sharpen the image, which when you're using unsharp mask, what you do is you create a mask for sharpening. The mask takes your original or your previous step here from up here, and then you create a mask by subtracting a blurred version of it. So I've taken the same thing, convolved it again with another Gaussian. This gives you a blurred version. You subtract it from here, and this is your mask. The mask then gets added back into the to the previous step, and that'll give you the sharpened image. If you take this and you rearrange your terms and pull out I sub x, I, x, y, what happens is you end up with the image function being convolved with a difference of Gaussian's kernel. And you can see this gives us the exact behavior that I described as being necessary for formation of Turing patterns, which is short-range activation and long-range inhibition.
So why can't you get Photoshop to just do the one step with the better distribution rather than having to go two steps?
Well, you can, but the Photoshop has a filter function that lets you give it a kernel,
Yes.
but the size is not that big, and so the kind of granularity of, so you can play around with it. It'll give you slightly different kinds of Turing patterns, but it is the same process. But typically, when you see people describing creating Turing patterns in the literature or online, in Photoshop, it's blur, sharpen, blur, sharpen. That's just the way it's been described. So another way to look at this is after one step of blurring and sharpening, we started with an image function I, now we have I1, which is, this is a slightly different way of writing what I had before, the difference of Gaussian. We can see that the solution to our generic model of a reaction diffusion equation, the solution to this is something like this, an image function convolved with a Gaussian, and then we needed some kind of nonlinear reaction function, and we have this here, plus there will be some other effects in Photoshop, like cropping pixels between 0 and 255. And so that's how you can see why blurring and sharpening would fall into the reaction diffusion model. So now I'm going to take a shift and bridge from math to art and talk a little bit about how I use Turing patterns in my paintings. These are a couple of images, let me back up, that are in paintings that are in the show here. On my website, I have a 4-minute video that shows how my paintings are made. I'm going to show you the super fast, super duper turbo 15-second version. Starts with an underpainting, then I paint a Turing pattern on it, then I do thousands and thousands of hand-painted little brush strokes of color, various different gradations of color to create color interactions. And eventually, when it's done, I have my Turing pattern painting. So again, if you're interested in the longer version, check out the website. For artistic purposes, choosing the initial seed is important. I guess a lot of people, since they're laughing, they can tell what the initial seed was here. So interesting, if you choose slightly different parameters, the enigmatic smile kind of fades away. I've used other famous pieces of artwork as source image for my own paintings. In this case, I started with Matisse's The Dance, ran it through this kind of process, and used similar colors from the Matisse painting for After the Dance. It's fun to start with tessellations or other geometric patterns. In this case, I started with a tessellation, put it through a 364 polar transformation, and used that as the starting seed for the Turing pattern that became this painting. You can grow your own Turing pattern. So here I'm starting with 2 circles, and if you run the Turing pattern process on it, you can end up with something really organic looking. Sometimes it's symmetric, sometimes the symmetries will just break enough to get something really interesting. That was the kind of process I used in this painting here. One of the reasons I like to use Photoshop as opposed to writing the software, I've done it in Python and C++, and there's plenty of tools also online for playing around with Turing patterns, but because I'm really familiar with Photoshop, and it gives you so many other tools along the way, like Twirl, the Twirl filter, where as the process is running, you can run one of these filters, and it'll sort of affect the general shape of the final Turing pattern, which you can use for artistic purposes to try and get some kind of meaning in there. For instance, this one I used the wave filter. Here, spherized to give it a sort of Vasarely-like kind of bulge in the middle. You can stop before you reach equilibrium, if you like the way that looks. In this case, this painting approaching equilibrium, I stopped the process about halfway before it had completely stabilized on a Turing pattern. And you can also use Photoshop for creative composition. So here I edited out portions of the Turing pattern and zoomed in and cropped to get exactly the kind of composition it had. It was a Turing pattern, but also had figurative kind of elements or things that can be read as figurative. I've used Turing patterns at multiple scales. So here in this painting, I have the same Turing pattern at 3 different levels, overlapping with painted transparency. And we have a painting called Multiple Drafts. This one's also in the show. I should mention here, back in 2010 at Bridges, Jonathan McCabe gave a great talk about using Turing patterns at multiple scales, a slightly different technique for creating his really beautiful digital Turing pattern images. And then finally putting it all together, this is one of my favorite pieces called The Eye in Disguise, where I started with a photograph of my eyes, created a Turing pattern from that, applied several different twirl filters as well as a pinch filter to create a sense of depth that doesn't show up so much on the screen, but does in real life, especially as the lighting dims. I think that's all I have time for. Maybe a moment or two of questions. Yes.
I noticed you were doing some of the small patterns by hand. How do you go from something great on Photoshop to something great like you've done in acrylic?
Those little patterns are technically not Turing patterns. They are just a personal mark that I've been drawing mazes like that since I was a kid, and I decided when I when I became an artist that I wanted to use that as the sort of framework for color. It's a sort of meditative kind of process that is fun to play around with.
But the overall larger pattern, you transfer it?
The larger pattern I transfer sometimes using a projector, sometimes freehand. Yeah. Other questions? Yeah.
How long did it take you to make these?
That is a very frequently asked question, and it depends very much on the size of the painting. So a small 12 by 12 might take a couple of days, whereas some of my larger ones, like the ones in the show, probably were 2 to 3 weeks to paint. Thank you very much.
You feel the questions well.
Yeah.
I was just going to say quickly on the stage of tweaking it with other filters along the way, or was that just you got to a certain point, stopped, and then did something, and then carried on from there?
A lot of times what I'd like to do is run the 10 times macro once, then apply like a twirl filter, then run the 10 times macro again, then another twirl filter, then again twirl filter. Actually, some really cool things happen if you run the twirl filter one direction, small amount, 5 times in a row or several times in a row, and then twirl it the other way after a Turing pattern. You get all kinds of really interesting dynamic shapes.
Have you tried plugging in filters or something? Maybe alien skin will give you good control for seeing those.
I can't remember if I've tried that one or not. I know that there are some that exist.
Are there any like area preserving properties of the process? Like, is the amount of do you know how the amount of black scales? I guess it looked like an increase in the circles, but
right. It won't preserve area because it'll actually foster growth. So if you started with just a small black spot and ran it, eventually you would grow a Turing pattern and fill the entire.
But it doesn't stabilize. It always stabilizes, or
if you choose these parameters, it'll always stay. Or most parameters with this process, it'll stabilize. Actually, it'll always stabilize in Photoshop. I think it might end up just a gray screen if you set the border too large or something like that. Thank you.